Welcome back everyone to the companion video on computing arcs or areas and arc lengths of polar curves. This is continuing our discussion on trying to answer calculus-based questions on these complex looking polar curves that were just introduced in the previous section. In the first part of this conversation, we introduced and formulated the formula for computing the area, quote unquote, the area under the curve for polar curves, which the formula we ended up coming up with was essentially computing the area between a polar curve and the pole, or the origin at 0, 0. And what we determined was that the area for one polar curve, say between alpha and beta, was indeed the integral between alpha and beta of 1/2 r squared d theta. And then the last thing we introduced is we said, okay, if I can do this for computing the area under the curve for one polar curve, how about the area between two polar curves? And it turns out that the answer is exactly what you want it to be. If r1 is below r2, then finding the area between the polar curves simply amounts to taking the difference of their two integrals. And so this is the formula we come up against. Once we have this power, we can now answer a bunch of more complicated questions. And that's going to be the primary focus of this video. Toward the end, we're going to introduce arc length and take a look at an example, and then we're going to look at a final question on computing vertical and horizontal tangent lines, something we did for parametric curves, but this time for polar curves, so we can again highlight that connection. To begin with, however, let's go over this example here. Here we have two different polar curves, r1 equals 1 and r2 equals 1 minus sine theta. In referencing your polar curve reference sheet, you should recognize this as a circle and a cardioid, respectively. Indeed, if I were to graph these two objects, what I'll find is that if I call r1 here in green, that's 1. This is just going to be a nice circle of radius 1. And then if I put r2 in orange, that's going to be a cardioid that shares the same points in the 0 and pi direction, and that's going to be a cardioid that points downward. And there we go. And then what we find is that if we're pointing in the 3 pi over 2 direction, we will recognize that if I plug in, for example, 3 pi over 2 here, I get a -1. So indeed, this is occurring at 2. And so the first question is, find the area of the region inside R1 and outside R2. So with these colors at our disposal, it's fairly easy to deduce what this is. Inside R1 would be somewhere within this circle. And outside R2 would be somewhere not inside the orange circle, which would be then something all the way around here. But specifically, it's also going to hit everything up here. Now the whole point is what got hit twice. We see that it's this little sort of crescent moon bit that got hit twice. And what we witness is that, in fact, for any ray that I take advantage of in here, notice that for any ray pointing in any given direction, notice that the upper curve is in fact R1 and the lower curve is in fact R2. And that's true no matter what ray I take. Again, upper curve R1, lower curve R2. As a result, what we see here is that the area in question is going to be equal to 1/2 the integral from something to something of r1 squared minus r2 squared d theta. And what are these angles? Well, in this case, it's fairly straightforward. We don't have to do any additional math. However, if you really wanted to figure out what angles these were intersecting at, you could figure what those intersection points are. The intersection is going to occur exactly when R1 equals R2, or equivalently when 1 is equal to 1 minus sine theta, or equivalently when sine theta equals 0, which occurs at exactly 0 and pi. So it turns out those are our correct answers, and indeed that matches with the picture. That's 0, that's pi. So indeed this is the integral from 0 to pi, which if we were to then compute what R1 squared and R2 squared were, we're going to end up getting just 1 minus sine theta squared d theta. And I'll let you go ahead and do, well, yeah. No, well, if we were to go through this, we would get, what, 1/2 times the integral from 0 to pi of 1 minus, this will FOIL into 1 minus 2 sine theta plus sine squared theta d theta, which will become, notice that the 1's will cancel, but we do need to distribute the negative. So this will become 1/2 times, here we're going to get the integral of sine. Well, let's actually run it all out. 0 to pi of 2 sine theta, and then sine squared with a power reduction formula is going to become 1/2 minus cosine of 2 theta over 2 d theta. And then maybe I'll leave it for you to finish off that computation from here. Now, for the next problem, we want to encounter the exact same functions, R1 and R2, except now we want to shade a slightly different region. Here we want the region inside both R1 and R2 at the same time. So what I'm going to do here is we're going to draw the exact same situation. That's a 1. We have a nice circle of radius 1 there. We have a nice cardioid. There we go. And what we want to do here is we want to find the area inside both at the same time. So that's going to be, for example, this tiny cardioid in the middle. Notice that for this tiny cardioid in the middle, depending on what ray we use, for example, if we are in the first quadrant, the area being contributed to the desired quantity, which is going to be that area, actually only encounters one of the two functions. It encounters everything up to right here, R2. It doesn't even encounter R1. Whereas, if I had a ray pointing down here, notice that it hits R1 first, and the area being contributed here is only coming from R1. So here the picture is really important, because here we're not actually computing the area between two curves. Here the desired area, due to symmetry, is going to be the sum of, well, it's going to be twice the area contributed by only this right half, for which the other upper semicircle, and you know what, maybe I'll even draw it like this just to make it clear. That's the upper semicircle plus the lower quadrant, where here we're going to get 2 times the upper semicircle is 1/2 times the integral from 0 to pi over 2 of R2 squared d theta, and the lower quadrant is 1/2 times the integral from 0 to pi over 2 of just R1 squared d theta. And then you'd have to compute these separately. So it's really imperative to make sure you draw an accurate picture and you understand what you're trying to go for, because sometimes you don't need the difference between two curves, whereas other times you do need the difference between two curves. So this is but an example in that direction. So let's press on and take a look at some more complicated examples. Here we have find the area of the region that lies inside. Now there is a typo here. I do want to write this as R1 squared. So keep in mind of that typo right there. Because the objective here is to figure out the area of the region inside one lemniscate while outside of another lemniscate. That's the objective here. And so here, it's imperative to have a super accurate picture of what's going on. For starters, let's go ahead and draw both lemniscates real quick. You'll recall using flat curves that we'll draw it like this. Here I want to draw R1 squared is equal to sine of 2 theta. If I were to draw that flat curve, I would have a sine curve. We'd have two of them, up to 2 pi. But I'm not allowed to consider the negative portion, so I only admit 2 petals, and the petals are going between, this is going to be pi, this is going to be pi over 2, and I start off here at 0. So when I translate that over to the polar world, I'm going to start off at 0, I'm going to stretch all the way out to 1 in the first quadrant, and then come back to 0, skip the negative petal, and then I'm going to build my next positive petal in the third quadrant, which is this petal, and then I come back and skip the fourth petal. So this is going to be R1, whereas R2 squared is going to be cosine of 2 theta. Again, we can draw the flat curve, what that looks like. It's going to start up here at 1, and we're going to get 1 cosine, 2 cosine, and end at 2 pi, where again, we're not allowed to have those negative petals. And so this is going to produce a lemniscate that starts over here at 1, produces, with this first part of the graph, it produces just half the first petal. So remember that. That's important for this computation, because if this is 2 pi, then that means halfway between that was pi, and a quarter of the way to the end of the first period is this bit right here, pi over 4. So this bit right here is pi over 4. And then of course we get the other petal right here, and then we come back to finish the first petal. What I'd like to do is overlay these two graphs on top of each other. Well, when I combine these two graphs together, what I'm going to end up with is let's zoom in here, I'm going to get one petal curve like this, and then I'm going to end up with, well, we're going to draw it in a slightly different color here, purple maybe, another petal curve that looks like that. So what we have here is R1 squared in purple and R2 squared in blue. And I'd like to know the area of the region that lies inside the diagonal lemniscate but outside the flat lemniscate. And we see here, if I shade this in yellow, what I'm asking for is the area of this region. I'm inside the diagonal lemniscate, but I am outside of the horizontal lemniscate. And the same thing is true over here on the right as well. Well, it turns out that the key to computing this area is observe that for an arbitrary ray that starts off here in the middle and goes off in any given direction, notice that if I run the ray all the way up here, this is above pi over 4, and therefore R2 has no contribution, but R1 does. So therefore, in that region, I don't actually need any sort of difference of two polar curves. Whereas, if we change that ray and made the ray stay right there, notice that we have an outside curve and an inside curve. Where the outside curve is R1, the inside curve is R2. But yet again, if we consider what's happening if I move down just a little bit more right here, notice that the outside curve is now the blue one, and the inside curve is now the red one. What that means is there are actually 3 different regions that I have to be considering here. There is the region that exists. So maybe we'll designate these region differences in black. There's the region that goes from this middle line downward. There's the region that goes from this line, and in between those two, and these two lines are cutting this entire picture into 3 regions. This first region, this second region, and this third region. The reason this is important is that this first region contributes nothing to the yellow desired area. The second region contributes a little bit of it, and the key thing is between those regions we have an upper curve and a lower curve difference. And then we have in the third region up here an upper curve, but the blue curve has no contribution for the lower curve. The key thing here is that the first line, this black one right here, is exactly when the blue lemniscate doesn't have any contribution anymore. But that's something we already understand pretty well. Right here, the blue lemniscate has no contribution at pi over 4. So this first black line here is theta equals pi over 4. The question is, what is this line right here? Well, that's occurring exactly when these two curves are equal to each other. And that is something that we need to solve for. So we can solve for the intersection. That is when R1 equals R2. Equivalently, when R1 squared is equal to R2 squared. Equivalently, when cosine of 2 theta is equal to sine of 2 theta. I wrote that a little backwards. This is going to be when sine of 2 theta is equal to cosine of 2 theta. And now it gets a little bit murky because there's a lot of answers that work for this. And so if you just go through methodically and figure out which ones work and which ones don't work, what we're going to end up finding is that here we'll get, and from 0 to 2 pi, we'll ordinarily get, in this case, the argument 2 theta is going to be equal to pi over 4 and 5 pi over 4. We, of course, want the thing that's happening in the first quadrant, so we are not going to care about that second one. And so when I divide by 2, I'm getting theta is equal to pi over 8, which matches what we had here. It's slightly smaller than pi over 4. So this is theta equals pi over 8. And so what that means is that the area that we're actually looking for here is twice the following sums. We're going to take this petal and we're going to add it to this weird partial petal. For which we get different formulas. So this is going to be 2 times the upper petal, which is only dependent on R1. So that's going to be the integral from pi over 4, well, 1/2 the integral from pi over 4 to pi over 2 of R1 squared d theta, plus this region's contribution, which indeed is going to be the upper curve, R1 squared, minus the lower curve, R2 squared. So that's going to be the integral from pi over 8 to pi over 4 of R1 squared minus R2 squared d theta. And I'll let you go through and finish off that computation. At the end of the day, if my math is correct here, we should get the square root of 2 over 2. But I wanted to take some time and work through that example because I think that it's very subtle what's happening over here in these petals over on the right. And this is where things like how the lemniscates are formed become really, really important. So let's take a look at another example. Here we're going to compare, again, 2 different polar curves. Here we have a dimple and a circle family. And so if I draw what these look like, what I'm going to get is I'm going to get, this is going to be a dimple pointing upward. So it's going to go all the way up to a 3 up here. It's going to come down to a 2, into a 1, and out to a 2. And so the dimple that we end up getting is something that looks like this. That's the upper portion, comes down, and then what it's going to do here, it's going to come back in, touch 1, come back out, and then connect like that. And then instead, this is a circle of diameter 3 that is tangent to the pole pointing upward. So that, if I underline that in purple, that's going to be this circle right here. And so for this, what I want is I want to know the area inside the dimple but outside the circle. And so if I zoom in here, that's going to be this region right around here. This is deceptively simple to compute. The inside region is just a circle of diameter 3/2. So therefore, the area in question here is simply computed by taking the area of the dimple, which is traced out once from 0 to 2 pi. So that's going to be 1/2 the integral from 0 to 2 pi of R1 squared d theta. And then subtracting off the area of a circle of radius 3/2. Well, that's just going to be pi r squared. Pi 3/2 squared. And so you don't have to use the calculus if you don't need to use the calculus. Again, here I'll let you finish the computation. By my computations, I was getting 9 pi over 4. So this just goes to show that sometimes the situation can be very complicated, and sometimes it can be very easy. But it all really boils down to accurately understanding what the pictures look like at any given moment in time. Let's take a look at one more example before we move on from this topic. Here we have 2 different cardioids, one pointing upward, one pointing to the right. And so if I were to take a look at both of their graphs, R1 is going to be a cardioid pointing upward. So that's going to be that. And if I were to graph in purple, R2, that's going to be a cardioid pointing to the right. And so if we draw that cardioid, it might look something like this. And I want to know what the area of the region that lies inside R1, so inside this blue one, but outside R2. So that means not in the purple. That means it's going to be this region up here. There we go. Notice that for this region, for most rays, for example, if I start here and I go all the way up there, the outside function is R1 and the inside function is R2. Similarly, if I point out in the left region over here, even if I point out right there, the outmost region is R1 and the innermost region is R2. So no matter where I look, the inner and outer curves are the same. The question is, where does this start and end? Well, it's going to start with this ray, because that's the intersection point. So that's going to be my alpha, and it's going to end with the other intersection point, which is right here. That's going to be our beta. To figure out what those are, we need to find out where they intersect. So the intersection is going to occur when R1 equals R2, or equivalently, when 1 plus sine theta is equal to 1 plus cosine theta, which, after the ones cancel, is asking sine of theta to be cosine theta. And we just saw this in the previous example. This occurs when theta is going to be pi over 4 and 5 pi over 4. So they should be opposites of one another, which tells me my picture is not completely accurate, but it's enough for us to get an understanding of what the picture looks like. So indeed, this turns out to be our alpha and our beta respectively, and since R1 is always the outside function, R2 is always the inside function, the area for this simply gets set up as 1/2 times the integral from pi over 4 to 5 pi over 4 of R1 squared minus R2 squared d theta. And again, this boils down to a trig integral using power reduction, which, if you go through that computation, you should get 2 root 2 at the end. So we've wrapped up our conversation on how to compute the area between two polar curves. That pretty much sums up the majority of the main content we wanted to talk about in this section. The remainder of this handout does have a brief discussion on arc length. However, I think that discussion is best left as an additional topic. If you're interested and you want to go take a look at it, I encourage you to work through the content, read through the section, and if you have questions, you're more than welcome to come visit me and we can have a conversation about it. The final object inside of this handout is a final question on horizontal and vertical tangent lines. This is a really interesting application of the content we learned earlier in this chapter. And the idea behind it is that if I have a curve, in this case r equals 1 minus sine theta, this is actually given parametrically in the form c of xy, where you'll recall that c of xy is the same as r cosine theta and r sine theta, where in this case r is well known as just 1 minus sine theta times cosine theta now, and again 1 minus sine theta times sine theta. And so if I wanted to figure out where the tangent lines are horizontal or vertical, this is going to be what I differentiate for my dx d theta. This is what I differentiate for my dy d theta. And I think this is a really great exercise in the tangent line and vertical line, the horizontal and vertical tangent line type questions, but this time using trig instead. And so I'll leave this for you to fill in the details, but you can verify that when you compute your horizontal tangent lines, you're going to end up getting theta values of pi over 2, 3 pi over 2, pi over 6, and 5 pi over 6. And when you compute your vertical tangent lines, you're going to be getting theta equals 7 pi over 6 and 11 pi over 6, as well as pi over 2, where pi over 2 in both of these is conspicuous, and therefore you need to use L'Hopital's rule to compute the limit as theta approaches pi over 2 of dy d theta over dx d theta. And if you were to go through this limit using L'Hopital's rule, you're going to end up getting infinity. Well, actually, if you use it once or twice, you end up getting something like 1 over 0, which is infinity. So theta equals pi over 2 is a vertical tangent line. But I'll leave it to you all to fill in those details, because I feel like this total video is already getting a little longer than I'd prefer. But this is going to wrap up our conversation in section 10.5. The next activity we have is the Polar Curvathon, so make sure to get as prepared for that as possible. But until then, that's going to finish all of our conversations in Calc 2. I hope you've had as much fun learning it as I've had teaching it. And if you have additional questions lurking in your brain as you continue studying for different assessments, be sure to reach out to me, come to my office hours, email me, and I'm always happy to help. But until then, I'll catch you all later.